Welcome students. So in last class we discussed about equations, differential equations of the following form: plus Rx y equals to 0, and we were discussing about solutions. So solutions at x naught, where p of x naught is not 0. Yeah, that basically had uh, the connection with the non-singular differential equations. Or equivalently, they were also given by the following. You had y double prime plus pxy prime plus qxy equals to 0, where p of x naught, where p and q were analytic at x naught, and we were looking at the power series solution at 0. Now we want to discuss about the other case where the solution, where we have the following differential equation: pxy double prime plus qxy prime plus rxy equals to 0, but we do not want the non-singularity, but instead we are looking at the singular points. So what is a singular point? So if you take this differential equation, it has singular point for value x equals to x naught if p of x naught is 0, provided x minus x naught is not a common factor of px, qx, and rx. Yeah. Or in other words, you basically need that if you write it in the following format: y double prime plus px y plus qx y equals to 0, then px and qx should not have a power series expansion at x naught, or they should not be analytic at x naught. So then we get the concept of singular points for a differential equation. So let's look at a few examples first. So example 1, consider 1 minus x squared y double prime minus 2xy prime plus y equals to 0. Now note that here we are taking px, qx, and rx to be polynomials, but they can be any analytic function in usual. So what we want is that if you look at this guy, this has singular points. Points are x equals to plus or minus 1. Yeah, why is that? Because this will make x equals to plus or minus 1 makes p of x 0. It makes this 0, but these are non-zeros, right? So these are non-zero. So therefore, x equals to plus or minus 1 is called singular point, right? Second, we have x minus 1 times 2x minus 1 y double prime plus 2x y prime minus 2y equals to 0. Again, you can see that singular points are x equals to 1 and x equals to 1 over 2. Why is that? Because again, here we have that px becomes 0 at these points, 1 and 1.5, but qx and rx do not become 0 at those points. Let's look at another example. So C 3. Let's take 2 times x minus 2 square x y double prime plus 3xy prime plus x minus 2 y equals to 0. Again, the singular points here are x equals to 2 and x equals to 0, because they, even though x equals to 2 is 0 here, but it's not a 0 throughout, right? So, and similarly, x equals to 0 is 0 here, but it's not 0 throughout px and qx and rx. So therefore, the singular points are x equals to 2 and x equals to 0. Now, fourth, let's take x minus 1 y double prime plus x minus 1 y prime plus x minus 1 cube y equals to 0. So in this case, you have p of x equals to 1 is 0, but then you can cancel, you can divide throughout by x minus 1, so there are no singular points. 5 x minus 1 square y double prime plus x minus 1 y prime plus x minus 1 y equals to 0. So in this case, we need to investigate this, particularly when we are discussing about uh, regular singular points. Yes, we'll come to that. So let's try to look about solving some particular kind of differential equation with singular points. Okay. So the first one which comes to the mind is the Euler's equation. So what is an Euler's equation? So you have basically, you have variable coefficients. So the coefficients are variable. Not only that, you have the equation is, it should be linear, it should be homogeneous, and should be ordinary differential equation, and should have variable coefficients. So such a differential equation is called Euler's equation. Okay. So now, once you're given this equation, question is it possible to transform this equation into something which we already know? Yeah. So we'll do the following. So we'll do the following transformation. Let x be e to the power t. In that case, we get what? We get t equals to ln x, and this means dt by dx is 1 by x, which is same as e to the power minus t. Okay, so then we get this thing, and now we'll substitute this in the equation. So therefore, what will happen for dy by dx? So dy by dx will look like dy by dt times dt by dx, and that is going to be dy by dt times e to the power minus t. Similarly, what is d square y by dx? So d square y by dx square is going to be d by dx of dy by dx. Yeah, that's the definition. So we have, this is going to be d by dt of dy by dx times dt by dx. And then that can be seen as, so this is going to be d by dt of dy by dx, which is dy by dt e to the power minus t times dt by dx. Now here in this part, we'll have to use product rule. So this becomes equal to d square y by dt square times e to the power minus t plus, sorry, minus e to the power minus t times dy by dt multiplied by dt by dx, which is minus t. And then it all simplifies to 1 by, so you can take e to the power minus t out. So we have 1 by t. So we have e to the power minus t out, e to the power minus 2t in bracket, we get d square y by dt square minus dy by dt. Now substitute 1. So substitute in the equation. So let's talk about it. So 1 here and 2 here. So substitute 1 and 2. But before that, let me rewrite this. This is going to be e to the power t is x. So e to the power minus t is going to be 1 by x square. So this is going to be 1 by x square d square y by dt square minus dy by dt. And similarly, this is going to be 1 by, this is going to be 1 by x dy by dt. So now we are changing everything to new variable. Given differential equation, so we get x square in bracket 1 by x square times d square y by dt square minus dy by dt. So this was your d y double prime plus alpha x. Now what is y prime? It's 1 over x times dy by dt plus beta y, which is going to be, what is y? So y is, well, y is y is equals to 0. So these guys cancel off, these guys and these guys, this guy and this guy cancel off. So what do we get? We get d square y by dt square. I'm going to bring dy by dx right away together. So I get plus alpha minus 1 dy by dt plus beta y equals to 0. Yeah. So therefore the solution is of form what? So we get this, right? So in this case we assume, so this is something we already know, right? So we can use, this is a homogeneous equation with a, this is a homogeneous differential equation, linear differential equation with constant coefficients. And then for such kind of differential equation, we always postulate the solution is of form y equals to e to the power r t, right? But note that what is your t? Your t is ln x. So we have y r ln of x, and that is going to be e to the power ln of x to the r. That's going to be x to the r. So the solution will be of form x to the r. So that's the idea behind it. So you convert it into a second order linear differential equation with constant coefficients. So let's work out an example. So here in this case, your x could be positive or negative, right? So you have to be careful about the absolute value sign. The solution to equation when x is greater than 0. So we have x square y double prime plus alpha x y prime plus beta y equals to 0. Now step 1, assume the solution is of form y equals to x to the r. Yeah, why is that? Because we got that idea from here. So we have y equals to x to the r, and then we have then y prime equals to x to the r, r1, and y double prime is going to be r into r minus 1 times x to the power r minus 2. So now plug it in the equation. So 2, plug it in differential equation. So when you plug it in differential equation, what do we get? We get x square. What is y double prime? R into r minus 1 times x to the power r minus 2 plus alpha x, y is going to be, y prime is going to be r x to the power r minus 1 plus beta x to the r equals to 0. Therefore, if you look at this, you can take x to the r common. What is left in the bracket? So r into r minus 1 plus alpha r plus beta equals to 0. Now, since x is greater than 0, x to the r is greater than 0 for all x, this implies r square minus r plus r, alpha r plus beta equals to 0. Or in other words, you're solving r square plus alpha minus 1 r plus beta equals to 0. Yeah, so this is an equivalent of characteristic rule, right? So what we do is we solve it using quadratic formula. Therefore r equals to minus alpha plus 1 plus or minus b alpha, so it will be b. So this is your a is 1, b is alpha minus 1, and c is beta. So I'm using the quadratic formula. So I get alpha minus 1 square minus 4 beta times 1 divided by 2. Yeah, so this is your r. So we have the solution splits like r minus r1, r minus r2 equals to 0, right? So now we have to just deal with 3 cases. So case 1, r1 and r2 are real and distinct. If r1 and r2 are real and distinct, we have y equals to c1 x to the power r1 plus c2 x to the power r2 is a solution, right? Is a solution, general solution. Case 2, r1 equals to r2 equals to a real. So we, in this case, we have y1 equals to r1 x to the power r1, and we need one more solution, so we can use reduction of order. Use reduction of order to find second solution. Now note that generally what you had you had e to the power r1t as one solution. Then second solution was e to the power r2t. Sorry, r1t r1t. Right. So this was solution. So what is your t? Your t here is, in this case, t is ln x. Right. So you can check. So homework. Second solution is y2, which is x to the power r1 ln x. Yeah. So therefore the solutions are y equals to c1 x to the power r1 plus c2 ln x to the power x to the power r1. Now case 3, we have complex roots. Case 3, we have complex roots. So what are the complex roots? So it's going to be so in this case we have complex roots. Yeah, complex roots for what? For this solution here, this equation here, right? So if we have complex roots, then we get that R1 be, so we get R1 equals to lambda 1 or lambda plus mu I. Then R2 is going to be complex conjugate, which is lambda minus mu I. And therefore, x to the R is going to be e to the power R ln x, which is going to be e to the power lambda plus I mu ln x, and that is going to be x to the power lambda cos of mu of ln x plus I sine mu of ln x. So this is your y of x is c1 x to the power lambda plus I mu plus c2 x to the power lambda minus I mu. And remember theorem, so recall, well, if you have complex valued solution, you can make it real, right? Because you are allowed to have this superimposition, yeah, solution. Then both real and imaginary part are solution. So what we'll do is the following. So we'll basically make it so we have y of x equals to c1 x to the lambda cos of mu ln x plus c2 x to the power lambda sine of ln x. So this is how we get to the solution. All right, so let's try to look at some qualitative behavior when x is greater than 0. Okay, so these are examples. So typically, so when you have two real roots, these are the different values of powers of x. So we have x to the power r, right? So this is how solutions look like. They all seem to intersect at 1. This is the solution for the second order when we have double root. So for example, the blue one indicates how the solution looks when it's x to the power 1 minus 1.5. The orange one indicates when the solution is of form x to the power minus 1 and so on and so forth. And the complex roots have, of course, oscillations in them. So you can see that when you have sine 4 log x to the power 0.2 and cos 4 log x to the power 0.2. So here log x actually is a short for ln x. So these are how the typical solutions look like. All right. So now let's discuss the same scenario with the Euler equation when x is less than 0. Okay. So now in this case, we may have, say, for example, x to the half, right? So It's not defined when what? When x is less than 0, right? It's not, what do you say? It's not real. Hmm? So we have to basically try to understand whenever we have x to the half, we will have, so it's defined, it's not real, right? It's not real when x is less than 0, right? So we have to bypass such scenarios using complex roots. So one way to deal with this is the following. So one way to deal is by the substitution x equals to negative t. If we have x equals to negative t, then we have what? T is greater than 0 when x is less than 0. And your y is solution yx is same as y of negative t. So you follow the same thing. So we have what? We have dy by dx equals to dy by dt times dt by dx, which is going to be minus dy by dt and then we have d square y by dx square is d square y by dt square, and in that case we get what? T square y double prime plus alpha t y prime plus beta y equals to 0 with t greater than 0. And to this equation apply the techniques we have learned here on the top, because our technique here was valid when x was greater than 0. So then again apply the solution. So what we get is, we'll get the following set of solutions. So when x is greater than 0 or x is less than 0, we'll redeem the previous method by just having an absolute value. So what we have is, that is, if x is not 0, the solutions are: 1, if roots are real and distinct, then it will be y equals to c1 absolute value of x to the power r1 plus c2 absolute value of x to the power r2. If roots are real and equal, then instead of usual t, you will have ln x coming into the picture. Y equals to c1 plus c2 ln of absolute value of x to the power r1, and complex conjugates. If the roots are complex conjugate, for the for the characteristic equation corresponding to this guy, so we get what? Y equals to absolute value of x to the power lambda c1 cos of mu of lambda absolute value of ln x plus c2 sine of mu of ln of absolute value of x. So the solutions are exactly the same way as the previous one, except you need an absolute value sign. So now let's discuss about, what about when we have solutions of the Euler equation when x is not 0. So this is the discussion then. Now we want to define what is called as definition of a singular point and singular regular point. So take p of x y double prime plus qx y prime plus rx y equals to 0. And consider the following limit. As x goes to x0, x minus x naught, qx by px. X goes to x naught, x minus x naught square, rx by px. Now, if these two limits are finite, then we say x naught is a regular singular point. So, for example, consider the following. We had 1 minus x squared times y double prime minus 2x y prime plus 4y equals to 0. You can see that x equals to plus or minus 1 are singular points. Here we have px is 1 minus x squared. And what is limit as x goes to 1 of x minus 1 times qx, which is, what is my qx? My qx is minus 2x, and my rx is 4. So limit as x goes to 1 of x minus x naught times qx divided by px, which is 1 minus x squared. And that is going to be limit as x goes to 1. I cancel the factors from here and here. I get minus 2x upon x plus 1 plus x, which is going to be, so I have 1 minus x, right? So this will become plus, and when I put x equals to 1, I get 1. Similarly, I get limit as x goes to 1 of x minus 1 square times minus 2x upon 1 minus x square. Sorry, what is my rx is what? Rx is 4. Sorry. So I get rx is 4. So plus 4 is limit as x goes to 1. And you can see that this will become, you cancel off the common factors first. So that will become, when you cancel the common factors, what you left out is with minus 4 x minus 1 upon x plus 1, and that is 0. So therefore, x equals to 1 is a regular singular point. Similarly, we can investigate. Similarly, we can investigate for x equals to minus 1. All right, so now let's look at another example. Example x cubed y double prime minus y equals to 0. Px equals to x cubed, qx equals to 0, and rx equals to minus 1. Now limit as x goes to, now in this case x naught equals to 0, as x goes to 0 of qx over px times, so limit as x goes to 0 of x times this is limit as x goes to 0 of x times x cubed divided by x cubed. And what is q of x? Q of x is simply 0, x minus 0 times this, which is 0 right away. But however, limit as x goes to 0 of r of x, so x minus 0 squared times r of x divided by x cubed is essentially, as x goes to 0, this becomes x squared upon 1 minus x, and this does not exist, right? Therefore, what do we have? So this limit is actually, so this limit is in some sense infinite, right? So what do we have is, therefore, x equals to 0 is not a regular singular point. And it's called irregular singular point. So note that all equations of form this behave very much like Euler equation near a regular singular point, and that's why we have this discussion. So note also, so note few important things. Why did we discuss this technique at a singular point? Y of x may not have a Taylor series. There are techniques about Laurent series, but we are not going to get in that. So now what is the goal? So goal is to adapt series solutions method for ordinary points so that it can be applied in neighborhood of in the neighborhood of singular points. Singular point, and that is what our next goal is, which we'll see in the next class. Thank you for your attention.